Okay, so welcome to the last session of the last day. All right. Thank you. And our first speaker is Hyeontae Jang from Ajou University, and he's going to talk about seeds with maximal Buchstaber number.
And I would like to thank the organizer to give me a chance to talk about my interests. This time I want to introduce what a seed is and the inequality involved in seeds with maximal Buchstaber numbers. Before doing those, I want to start with recalling the Buchstaber numbers. For a simple linear complex with m vertices, the Buchstaber number is defined as the maximal number, which can be the dimension of a freely acting subtorus on the moment angle complex of K. This invariant has a general bound. This is at least one and at most m minus n. And this upper bound is also called the Picard number of K. And maybe I will write this peak of K or P. For a p-dimensional freely acting subtorus, the quotient of the moment angle complex by this action covers many interesting cases, such as quadratic manifolds or topological Turing manifolds, depending on the structure of K. These complexes are properly contained in the class of PL spheres. So in this talk, I want to focus on the class of PL spheres. For a subtorus H, we can represent the action by an M by P matrix S, whose entries are these coefficients Sij's. And in this matrix, I want to define a P by P matrix as sub sigma complement. This is a submatrix of S whose rows correspond to the complement of sigma for each process sigma of K. Then this action acts freely if and only if the determinant of S sub sigma complement equals plus minus 1 for any facet of K. Then to define seed.
So when you say subtorus, you actually mean consistent with a given splitting? When you say subtorus, do you always mean consistent with a given splitting?
I don't understand.
So the torus can be written as a product of circles,
Yes.
but some subtori are not products of these very same circles. But do you restrict your attention?
Maybe.
So it's any subtorus here.
Yeah.
Okay, thank you.
Now to define seed, we need J construction. The J construction K of J is the simple linear complex obtained by duplicating its vertices V into JV copies in each minimal known face of K. And we can consider K as a subcomplex of K of J by identifying each vertex V to one of its copies. For example, just for V1. And for example of the J construction, if we have pentagon at the boundary of pentagon, then we have 5 minimal known faces, and the J construction K of 2, 1, 1, 1, 1 contains 5 minimal faces, and 1 become 2, 1, 1, 2 ones, 2 copies, 1, 1, 1, 2, and the other same. J construction preserves nice structures of K, original K, Pierce-Fairness, polytotality, or star-shapedness, and Picard number and the Buchstaber number are same. Moreover, any subtorus freely acting on the moment angle complex of K of J can be constructed by subtori freely acting on the moment angle complex of K. Keeping these good properties in mind, we can define an essential PL sphere. A PL sphere K is called a seed if it cannot be obtained by non-trivial J construction. For seeds with maximal Buchstaber numbers, there is the number of vertices M has an upper bound for each fixed Picard number. This is because for a freely acting subtorus represented by an M by P matrix S, this is just a fact I will use now. For a seed, the rows of S have to be mutually distinct. And then the March reduction of S should also not allow repeated rows. And because this is a March reduction, the vectors are Z vectors of length P. So the number of rows M have to be less than the number of Z2 vectors of length P. And from this inequality, I want to talk about the converse. Actually, the converse is true. Moreover, in particular, this inequality is tight, and this is moreover true for the class of polytopic complexes, not just for PL spheres. So there is a quadstring manifold over a seed with appropriate and M we're interested in. To prove the theorem, I want to introduce a construction, but to do that, I have to say suspension and some other construction. Firstly, for suspension, the suspension of K is obtained by adding 2 new vertices and forming 2-sided cones with these 2 vertices, like this. Then suspension preserves the structures of K, Pierce-Fairness, polytotality, and the star-shapedness. But this increases the dimension by 1, but the number of vertices by 2. So Picard number and Buchstaber number are increased by 1. And K is a seed. If an olive, the suspension is also a seed. Yeah, so, and the stellar subdivision of K is made by with 3 steps. Firstly, picking a face, sigma, and then if it choose this edge, then add a new vertex in the relative interior of this face and triangulate minimally. But this one is actually same to the suspension of K. So we have the first property that this is a seed because the suspension is a seed, if K is a seed. And the scalar subdivision also preserves structures of K except for portability, but yeah, preserves the portability in one direction. And because this operation add one new vertex, but without changing dimension, so the Buchstaber number and the Picard number are increased by 1. So this is our construction. Firstly, choose any subset sigma of the vertices of K. This is not necessarily a face of K. And then let's trace of sigma equal positive integer tuple with 2 and 1s, 2s and 1s for each JV equal 2 if V is in sigma and 1 otherwise. Then we can directly compute that sigma is the face of K of J sub sigma. And yes, actually this is K of J operation duplicating each vertices in sigma into 2 copies. And then if we subdivide the stellary at this sigma, because sigma is a face, this is a seed if K is a seed that is not a suspension, and sigma has at least 2 vertices. From this, we can make all other PSP or other seeds with maximal Buchstaber numbers. From here, for Picard number 3, we know that there exists exactly one polytopic seeds for each appropriate dimensions, and if we know the polygons always have maximal Buchstaber number, then here we can make by suspension these 3 ones, and here from here we can make our construction all of these things with 2 2 1 1 1 1 like 2 2 2 1 1 1 1 like this. And I want to remark 2 things. The maximal one is the doubling operation followed by the bistellar subdivision from the maximal complex with previous Picard number. So this makes the tightness of the inequality. And for Picard number 4, actually there are 4 C's here, and this is one of the complex. And I want to ask, I wonder that the others are polytopic or not, and this because this is a polytopic. And for completely non-singular fans, this inequality is not tight. Actually, for Picard number 4, I already calculated for seeds, whether seeds admits a non-singular complete fan or not, and n is at most 8. But our construction gives from Picard number 3 n equals 7Ks, but this is because the second one of Picard number 3 is suspension. So we cannot apply our operation. But here, Picard number 4, we can apply all of dimensions. In all of dimensions, our construction. So I want to see that from this, for Picard number 4, our construction gives the maximal dimensions for each Picard numbers. Thank you.